Hey everybody, we're going to continue with the light unit, and today we're going to talk about reflection and start talking about mirrors. So I've got a few pictures here of reflections. We got the otter with his reflection in the water, the girl in the mirror, the guy looking in the DVD, the reflection off the lake of the mountain, got a hubcap. We're going to talk about that type of mirror tomorrow. And then this woman taking a selfie in a mirror. So you're pretty familiar with reflections. You've been seeing reflections your whole life. You see reflections every day, so it's nothing new. I want to look at this girl taking her selfie. So she is taking the picture in a mirror. So this hand right here, which is on our right, would you say that's her right or her left hand? Okay, well, I just told you she's looking in a mirror, so you're probably saying, well, that's her right hand because we're looking at the mirror image, all right? But if I didn't tell you she was looking in a mirror and you couldn't see the curved part of the mirror here, if I found a better picture, if I didn't tell you that, would you know which hand is which? You'd probably say this is her left hand, thinking that she's facing us. So mirrors do this thing where they switch left and right, or it appears they switch left and right. But do they switch top and bottom? I mean, her head is on the top and her feet are at the bottom. You know, we can't see any flip that way, but we do see that left to right flip. Now, I'm not going to explain that in this video. I want you to think about that. Instead, I put a couple links to other videos that explain it a lot better than I ever could. One is the physics girl. She does a good job of explaining this. And then the other is Richard Feynman. I don't know if you've heard that name before, but he's a very famous scientist. Won the Nobel Prize actually in science. So he also explains it, and they explain it pretty much the same way, but you know, a little difference here and there. So anyway, check those videos out as well. Okay, so moving on. All right, law of reflection. Reflection does have a law to it. So let's say we have a mirror here just sitting on a table, and then we're going to shine light on it, let's say from a laser pointer. So we call that the incident ray. And then that, of course, is going to reflect off the mirror, and you can all tell me which direction, general direction that's going to reflect, and you'd be right. Okay, so we've got the reflected ray. It's a lot like bouncing a ball, like a bounce pass in basketball or something like that, or vectors, really. The x direction is not changed, but the y direction, it does bounce off that way. Okay, so now you could probably tell me that, well, it's probably equal angle coming in as is going out. So let's identify these angles first. First, we have to look at a normal line. So a normal means perpendicular, and it's perpendicular to the mirror surface. This is going to be important, this whole unit. We're always measuring angles with respect to that normal, that perpendicular line. So let's label them here, theta I for the incident angle and theta R for the reflected angle. And then the law of reflection simply says the angle of incidence equals the angle of reflection. Very straightforward on that, pretty simple. Theta I equals theta R. And remember, the angle is always measured with respect to that normal line. That's very important going forward. That's really it for the law of reflection. Now, there are two types of reflection. First is called specular reflection, and that is reflection off a smooth surface. Smooth surface meaning like a mirror or a glass or a very calm lake. Your cell phone, before you turn that on, you look at it, you probably see a reflection of your face in that. That's specular reflection. So how that works is you have these light rays coming in parallel to each other, and they're all going to reflect. They all obey the law of reflection, and because this is a very smooth surface, if they're coming in parallel, they're going to reflect parallel at the same angle. That is specular reflection. The other type is diffuse reflection, and this is reflection off a rough surface. What's a rough surface? Well, anything that's not very smooth, really. So there's a lot of things that could be that. But anyway, what happens here is you can see this surface is not as smooth. The incident rays, they're all coming in parallel, but then they hit different points on that surface. And because that surface has a lot of dips and bumps in it, each ray is hitting a different, I guess, angle of surface there. So each ray is obeying the law of reflection. Okay, if you look at any individual ray, it's obeying the law of reflection, but because they're hitting surfaces at different angles, they get scattered like that. So you get a mess. They're not parallel coming out. So a couple examples. Here's specular reflection, a mountain in a very calm lake. You see a very clear image with that. That is specular reflection. And then here we've got a lake. It looks like the wind is blowing or something. And you can see the reflection of the trees in there, but it is not a clear image at all. It's just a blurry mess. So that'd be more diffuse reflection. A couple more examples. I just did this one earlier. So I'm holding up a sheet of paper and I'm holding it vertically. And then on the other side of the sheet of paper, I have a laser pointer. And I'm shining that laser pointer down to the table. In this case, there's a mirror laying on the table. So I'm shining that laser pointer on the mirror and it reflects back up to the paper. So we see that nice clean dot there. Okay, again, I'm not pointing the laser directly at the paper. I'm pointing it at the mirror on the table, reflecting up onto the paper. Here I'm just pointing on the table. So I remove the mirror. I'm just pointing on the table. The table's pretty smooth, but microscopically it's got a lot of those bumps in it. So I'm pointing at the table, reflects off that rougher surface onto the paper, and you see that fuzzier dot there because those light rays are all getting scattered about. Okay, so images formed by plane mirrors or flat mirrors. That's what we're going to talk about today. Flat mirror, plane mirror, it means the same thing. Okay, so here is a chess piece and then somebody looking at that chess piece. I don't know who does this, but this could be your chin or your belly button or something you're looking at in the mirror. So anyway, in order to see an object like this, they don't emit light. You have to have light incident on it and it reflects off, and that's the light we see. So we've got a light fixture somewhere in here. It's reflecting off this piece. Now it's reflecting in every direction imaginable. Okay, and we could draw those rays in there, but we don't care about all those rays. We just care about the one ray that's going to reflect into our eye. So it has to obey the law of reflection here. So we're only going to draw this one ray in, hits the mirror right here, goes into the eye. So as the eye sees it, it just sees this light ray coming at it from this direction. Okay, it does not see the light ray down here at all that's going into the mirror. It just sees the light ray coming from the mirror. So it looks like it's coming from way over on the other side of the mirror if you follow that apparent path of the light ray. All right, so that's a characteristic of a plane mirror. All right, so now let's look at another image here, and I got this from the physics classroom website, but this is a man right here looking into a mirror and seeing his image. So in order to see his foot, again, you've got light shining on the foot. It's reflecting in every direction, but we just want the light ray that's going to reflect off the mirror and into his eye. So again, angle of incidence equals angle of reflection. We've got the law of reflection going on. So the blue ray is reflecting off his foot into the mirror. That's the incident ray. And then the red ray is the reflected ray. We can also look at the top of his head, or he can. Okay, so you've got a lot of light hitting the top of the head. We're going to look at the one ray reflecting into the mirror and back into his eye. So if we follow these reflected rays, these red rays back, that's where it appears the image is located, on the other side of the mirror. Now, I'm pretty sure you guys can see that. If not, pause right now, go to your bathroom, look in the mirror. Does it look like your image is right on the mirror, or does it look like it's beyond the mirror? And in my history of teaching, students say, yeah, it looks like it's on the other side of the mirror for sure. And we know this for a couple of reasons. One is in life, we know things that are farther away appear smaller. It's that perspective thing. It's like if you look at somebody across the room, and you hold your fingers up like there and put their head in that space between your thumb and your finger, and then squish them a little bit. Their head obviously is not that tiny, okay, but it looks that small because they're farther away from you. So when you look into a mirror, you see what appears to be a smaller image. So there your brain thinks, okay, it's farther away. All right. Now let's put some dimensions on here. So HO, HIDI. So HO is called the object height. HI is the image height. DO is called the object distance. That's just the distance from the object to the mirror. And DI is the image distance, the distance from the image to the mirror. So with flat mirrors, what happens is your object distance and your image distance are the same. All right, and I've got a demo that we could do if we were in school. We could show that, but it does work out that way. So if you're 3 feet in front of a mirror, it looks like your image is 3 feet on the other side of the mirror, so 6 feet away from you total. All right, so, and again, because something's farther away, it looks smaller. All right, if you had an identical twin 6 feet away from you, you would think, okay, it's the same size as me, same height and everything. Same thing is true with a flat mirror. So the image height is the same as the object height. If you don't believe this, if you have a full length mirror that works best, stand, as far away as you can and then walk towards it. Once you get right in front of it, you see that that image is the same height as you. So that image size and object size are the same. Now, another thing here is how much of the mirror you actually need to see your image. So if you look, this guy only needs from this distance from X to Y, they have it labeled. Turns out that's half the person's height. And if you think about it, it makes sense. So the point Y is halfway between the guy's foot and his eyeball. Okay? And then the point X is halfway between the top of the guy's head and his eyeball. So if you add that up, you only get half the person's height. Okay, you get half of the height from here and half of the height from there. So that's half the total height. It's like if you were looking through an open window and your identical twin was on the other side of that. It'd be possible to see their whole image if, and you would just need that window space there. Okay, now another thing I want to point out is it doesn't matter how close or how far away you are from the mirror. A lot of people think, oh, if I get farther away, I would need less or more of a mirror. Doesn't matter. The geometry works the same either way. Doesn't matter how close or how far you are from the mirror. You only need half your height of a mirror to see your whole image. It has to be at the right position on the wall, but you just need half that height. Okay, so object distance equals image distance. Object height or object size equals image size. So a quick summary here. Law of reflection states that the angle of incidence equals the angle of reflection. Types of reflection, we have specular, which was off a smooth surface like a mirror, and diffuse reflection, which be off, a lake that has little waves on it, or reflecting off a table like I showed in that one picture. For flat or plane mirrors, the object distance equals the image distance, and the object height equals the image height. And to see your whole image in a vertical flat mirror, you need a mirror that is half your height. Okay, that's it for today. Let me know if you have any questions.